Section 7.4 in Chapter 7 of your textbook discusses the wave nature of matter. Included among these things are the deBroglie wavelength, the uncertainty principle, and indeterminacy. So by the wave nature of matter, what they're talking about is that everything is both a particle and a wave. This is the new quantum mechanics where we have to treat everything as both, that a long time ago we didn't notice because our instruments couldn't measure the differences. So how do we know that things are both a particle and a wave? The photoelectric effect, discussed in another video, talks about that a little bit. I also now want to bring up what we call the deBroglie wavelength. And there's an equation for that. Wavelength is the symbol lambda. And in this equation, lambda is equal to h over mv. This is an English letter v, not the Greek nu for frequency. So lambda is wavelength. The h in this case is Planck's constant. And the m is mass. And the v is velocity. So if you think about mass, if something is heavy, it has mass, that's a particle property. But when you look at wavelength, that's clearly a wave property. So this equation relates wave properties to particle properties. How did this equation come about? What did deBroglie do to get to this point? Well, what he did was he shot X-rays, which we traditionally think of as waves, at electrons, which we think of as particles. When the X-ray hit the electron, it knocked the electron off, flying in a different direction, as though the wave was just another particle. For example, if you're playing pool or billiards, one ball hits another ball and it sends it off flying some other direction. That's how these behaved. And the wavelength of this X-ray imparted momentum onto the particle, making it move. Another way to think about momentum is that it's mass times velocity, and of course in this equation we have mass and velocity. So the wave imparted momentum on the particle as though it were just two particles, and how much momentum it imparted depended on the wavelength of that particle. So this clearly relates wave and particle properties. You might wonder, why don't we notice the wavelength, the wave properties of particles that we can see, like a baseball or a car or an airplane? Well, the answer is actually pretty simple once you do one of the calculations. So let's say that we have a baseball, and let's say this ball weighs 250 grams, about the size of a baseball. And let's say that, and that's our mass of the baseball. Let's say it's thrown, and we have a really good pitcher, and he throws it at 95 miles per hour. And we want to calculate the wavelength of that ball. Well, we jump down and we grab the deBroglie equation. Lambda is equal to h over mv. We plug in Planck's constant, 6.63 times 10 to the negative 34th. We plug in mass, 250, and we plug in speed or velocity, 95. And I punch these numbers in, and I get the wrong answer. On mastering chemistry, the homework, if you'd punch that in, it'd give you a big red X. And it's not because I was using, I looked up the wrong numbers. One thing you might have noticed is that I did not pay attention to units in this problem. And if we look at the units of H are energy units, joules, times time units, seconds. The units here for mass are grams, and the units here for speed are miles per hour. And you might notice that none of these units cancel. Joules, seconds, miles, hours, grams are not going to work. So the problem is that we had the wrong units in here. The first step in trying to improve that is to look at the unit of joules. And in your book, it says joules can be broken down into other units. If you take physics, you'll learn why that is the case. And it has to do with force and distance and work and energy, that kind of stuff. But essentially, in your book, they tell you that a joule is a kilogram meter squared per second squared. So if I take this value here, or those units, and replace them, or replace joules with those, I could rewrite the equation going lambda equals h over mv, 6.63 times 10 to the negative 34th. And again, instead of J, I'm going to write kilogram meter squared per second squared. This other seconds is still there, so that's still there. And now it's more clear to see that the 250 gram number needs to be in kilograms. And if you do that conversion, 0.25 kilograms, the miles per hour, instead of miles, this has meters in there, so it needs to be meters on the top. And instead of hours, you'll see the seconds all over the place, so that needs to be in meters per second. And if you convert 95 miles per hour to meters per second, you get 42 meters per second. I would encourage you to make sure that you can do these conversions on your own. And now, when we plug in these numbers, I went ahead and plugged them in, and I got 6.3 times 10 to the negative 35th. If we look at our units, kilograms on the top cancels kilograms on the bottom. This seconds cancels one of those two. The other 1 over seconds is canceled by this 1 over seconds. And finally, the 1 meter on the bottom cancels 1 from the meters squared. So the only units left here are meters. So why do we not notice the wavelength of a baseball? Well, that's a really small number. It is that many zeros after the decimal place, meters. 10 to the negative 35th is crazy small. And that's why we don't notice the wavelength of things that are big enough to see. So if the mass on the bottom is big enough for us to see, the wavelength ends up being too small for us to notice. So that's one of the reasons we don't notice that here. I would like to continue and mention also another phenomenon here. And the next thing in this section talks about Heisenberg's uncertainty principle. Heisenberg's uncertainty principle can be written in equation format. Delta x times m delta v greater than or equal to h over 4 pi. So here's what I think is important to recognize about this. First, delta x, delta, the Greek triangle letter delta, usually represents change. Here it's uncertainty. So delta x is the uncertainty in position. So x being like the x-axis position. M stands for mass. And delta v, again, the delta v is uncertainty. But this time it's uncertainty in velocity or speed. So On the left side, we have uncertainty in position times mass times uncertainty in velocity. This whole thing right here, h, is Planck's constant. It's a really small number, 10 to the negative 34th. 4 is a number, pi is a number. So essentially, this is a very small constant number. And all this stuff on the left has to be greater than or equal to greater than sign this small constant number. So what does that mean to us? That means that uncertainty must be larger than tiny number or another way to say that, you cannot know them exactly. So the uncertainty has to be more than zero uncertainty, or the easiest way to say it is you cannot know exact position and exact velocity at the same time. And that's how this is often represented. You cannot know the exact position and exact velocity at the same time. The position part should make some sense, because if everything is a wave and a particle, a wave doesn't have an exact position. Another way to think about it is, normally when we look at an object, so say we have some object standing here, the way that we see it is light hits it, is reflected off, and that is what our eyeball sees. Now, that's fine if it's a big object. The light doesn't really influence a big object very much. But if you have a tiny object, like something as small as an electron, and light comes in and hits that electron, it's going to knock the electron off flying. So it used to be perfectly still. We knew the position. Once we measure that position, it changes the velocity by shooting it off in some other direction. So we can't know both of these at the same time. Another way that this is often represented is, you might remember in the equation, it gave mass and uncertainty and velocity. If you know the mass and the velocity, you also know the energy. So some people say it's position and energy you cannot know exactly, instead of position and velocity. If you're going faster, you have more energy. So you might see in a different book, instead of saying velocity, they would say energy. Now, last thing that I want to mention about these, since we can't tell exactly where it is, the Bohr model of the atom, where you have a positive nucleus and the electron is traveling around in these exact orbits, does not work. So again, this is the Bohr model. Bohr violates the uncertainty principle. Because if we know this exact orbit, that tells us we know the exact speed and velocity. So instead, is we no longer say an orbit. We don't use orbits anymore. Instead, what we say is orbital as the most likely place to find the electron in the atom. So since it's most likely, it's not exact, it's just probabilities. And so if we go back and put in the positive proton in here, every time we say we do the quantum mechanical calculation to find out where that electron is located, every time we do the calculation, it's in a different spot. We do the calculation once, twice, 3 times, then we plug it into our supercomputer to figure out this place, and over time, we get a picture of where we are likely to find the electron. Every one of these dots is a different calculation. And it's not always necessarily where we expect it to be. But if we keep making these calculations, we find that over time, it's very clear that the electron is mostly found here and here. So some orbitals have this dumbbell shape where the electron is just said to be somewhere in that space. So this dumbbell shape is often referred to as an orbital, the most likely place to find it. Some orbitals are dumbbell shaped like this. Some orbitals will instead be spherical around the nucleus. So you might see the area you're likely to find it is this spherical shape somewhere around the nucleus. That's different orbitals.